Hello everyone, my name is Plamen Nikovsky and I work in the Department of Electrical Engineering and Electronics in the University of Food Technologies in Plovdiv. Now I try briefly present my work about multi-sensor configurations in data fusion systems. Sensor fusion is a process that combining sensor data to obtain a result considered better than one obtained from individual use of the sensors. Figure shows a simplified block diagram of sensor fusion system. It consists of the sensors Q sub 1 to Q sub n, where n is greater than or equal to 2, and a processing module PM implementing the process of combining the observation x sub 1 to x sub n, called source variables or sources. In many cases, the result from the fusion B hat is an estimate or prediction of some variable B, target variable, associated with the object under observation O. The choice of sensors is one of the most important moments in sensor fusion design. It is difficult to find a solution to this problem without clearly defining those common features showing how similar or dissimilar the sensor configurations are. The present paper attempts to define such features based on the specific information interaction between the source and the target variables and considers the possibilities for their use as criteria for classifying sensor configurations. This paper is organized as follows. First, the known criteria used to classify sensor configuration are considered. Then, in section 3, we introduce the partial information decomposition, PID, proposed by Williams and Beer. In section 4, PID was used to define new quantitative criteria for the classification of sensor configuration. Finally, conclusions are summarized in section 5. Sensors are key element of sensor fusion system which provides the information needed to achieve the goal of data fusion. Looking for unified description of sensor capabilities in multi-sensor system, Darren outlines three basic types of information interactions: complementary, competitive, and cooperative. Complementary information interaction occurs when two disparate sources provide information which together provide a more global view of environment but which do not overlap by themselves. Competitive information interaction occurs when two sources provide the same piece of information and a joint consensus must be reached. Cooperative information interaction is the case when one information source must rely or cooperative with another in order to obtain observations. Often, the criteria and categories for classifying sensor configurations are also used directly to classify the data fusion process. Beder-Wissing and Bishar defined competitive sensor fusion as the fusion of data from sensors with the same modality. Combining sensor data according to a predefined physical model that enable the sensor outputs collectively to estimate the state of higher level measured physical process is a complementary type of sensor fusion according to Wu. More definitions can be found in the study and the cited references. The literature review illustrates the fact that problems arise when using the currently known information criteria for classifying a sensor configuration. They can be summarized as it follows. Many of the terms and expressions used in the definitions are specific and allow subjective interpretation. Global view, environment, joint consensus, more complete image, not directly depend, etc. This makes the definitions difficult to understand and often leads to confusion. Although the main topic is information, no attempt has been made to define the information interactions through terms and concepts used in the classical information theory. The definitions of the information interactions do not directly mention the target variable. However, if the configuration of the sensors in the fusion system is not determined in context of the target variable, this may lead to ambiguity. The current classifications are primarily of theoretical importance, as there are no proposed procedure that show how to apply them in practice. The partial information decomposition, PID, proposed by Williams and Beer is a very recent extension of the Shannon information theory. The authors are convinced that information interaction between the random vector x and other variable b can be fully described by introducing the information theoretical concepts of unique, redundant, and synergistic information. Briefly, these concepts can be presented as follows. The information that x1 provides about b but x2 does not, or vice versa, is unique information. When both variables x1 and x2 provide about b the same or overlapping information, it is denoted as redundant information. The information which the variables x1 and x2 together have about b, but which cannot be obtained by observing them separately, is synergistic information. Once the basic definitions have been introduced, the equation representing the main idea in the PID can also be written. For a system with three variables, the total amount of information provided by the sources x1 and x2 about the target variable b is equal to the sum of the following four non-negative terms, where I is the mutual information between set x1, x2 and b. U1 is the amount of unique information that x1 conveys about b. U2 is the unique information that x2 conveys about b. R gives the redundant information shared by x1 and x2, and S is the synergistic information that x1 and x2 in combination have about b. This concept itself can be also applied in cases where the number of sources is greater than 2. The PID method gives a complete picture about information interaction of target and source variables. According to the information that the sensor data x1 to xn provide about the target variable b, the following new types of definition can be proposed. Complementary sensor configuration. A sensor configuration is called complementary if the amount of unique information provided by each sensor observation about the target variable is other than 0. Redundant sensor configuration. In this case, the amount of redundant information provided by the sensor data about target variable is non-zero. Cooperative sensor configuration. A sensor configuration is cooperative if the amount of synergistic information which the sensor data provide about the target variable is non-zero. The proposed classification has several significant advantages. The classification is directly related to the information theory and uses generally accepted definition and terminology. Qualitative criteria are replaced by quantitative criteria in this classification. The configurations are divided into classes based on the amount of information, which is a measurable quantity. In addition to ensuring objectivity, this allows for direct comparison and evolution of different sensor configurations. Currently, a number of software packages with the functionality estimate partial information terms can be found. Numerical methods in them can be used to create a real procedure for sensor configuration classification. The present work proposes new criteria and new type of classification defined within the framework of the partial information decomposition, a recent extension of the information theory. Each criterion is a term of the decomposition quantifying a specific amount of information between the source variables, the observation of the separate sensors, and the target variable, the variable to be found by fusing the source variables. The proposed criteria, unlike the exciting ones, are quantitative, ensure objectivity in classification, and allow for direct comparison and evaluation of different sensor configurations. Thank you for your attention.